It is an honor to present our work, CriSp, leveraging thread depth maps for enhanced crime scene shoeprint matching. This is a joint effort between the University of California, Irvine and the Texas A&M University. Shoeprints are one of the most common kind of evidence found at crime scenes. Identifying the make and model of the shoe that left a print at a crime scene can help forensic investigations by narrowing down suspects of a crime. Occurring Analyzing the crime scene shoeprint images is inherently challenging because of their degraded nature. They are often noisy, occluded, and only partially visible. They can also occur across various mediums. Given a query crime scene shoeprint, we aim to provide investigators with a ranked list of potential shoe model matches. Traditionally, crime scene shoeprints are compared to a small and manually curated reference database of shoe prints. We propose to match crime scene prints to the thread depth maps in a large-scale and automatically generated reference database of thread images downloaded from online retailers. To study this problem, we introduce some training and validation sets. We generate a training dataset consisting of thread images downloaded from online retailers and their depth and print estimates obtained using an off-the-shelf predictor. To evaluate methods, we introduce a reference database and two validation sets. Query shoeprints in our validation sets match to thread depth maps in the reference database. The reference database is a superset of our training data. Our validation set, val-FID, contains real crime scene shoeprints from the FID 300 dataset, while val-Shoecase contains simulated crime scene shoeprints using blood and dust from the Shoecase dataset. Note that all the depth maps and prints are globally aligned in all our datasets. Even for partial prints in the val-FID dataset, we translate, scale, and rotate them as needed and place them on a shoe outline to ensure alignment. Our method, named CriSp, first predicts thread depth maps and clean, fully visible prints from RGB thread images. Then, a data augmentation module simulates noisy and degraded crime scene shoeprints from the clean prints by optionally using occlusion, erasure, and noise. Occlusion is added in the form of overlapping prints and random shapes. Erasure removes part of the print to create a grainy appearance, and the noise mimics background clutter in images. We can see the effects of each of these degradations and example simulated crime scene prints here. Next, we apply random rectangular masks on our simulated prints to mimic real crime scene prints, which are often only partially visible. Our encoder generates feature representations for both thread depth maps and shoeprints. The encoder is a modified ResNet 50, where the last pooling operation has been removed to output spatial features. The spatial features allow access to different coarse locations on the thread depth maps and shoeprints. Since our training and validation data are globally aligned, we can match shoeprint patterns to corresponding locations on the thread depth maps. We enhance retrieval performance further by applying our mask to the spatial features. This helps CriSp focus on the visible regions on the crime scene print. Our method is trained using the supervised contrastive loss, and similarity is measured using the cosine similarity. CriSp performs very well in retrieving the best matching shoe models to query crime scene shoeprints. Here we see the top 10 retrievals by CriSp on val-FID and val-Shoecase. CriSp retrieves positive matches very early, even when crime scene shoeprints have very limited visibility or severe degradation. Additionally, corresponding locations on the retrieved shoes share similar patterns to the query print even in negative matches. We compare CriSp to state-of-the-art on automated shoeprint matching and on image retrieval methods tailored to this task. Assuming an investigator would look through the top 100 retrievals, we report the standard ranking metric mean average precision at K for K equal to 100 or MAP at 100. The MAP at 100 values show that CriSp consistently performs significantly better than related work on both our validation sets, including the blood and dust categories within val-Shoecase. Thank you for your attention. Please visit our poster to learn more.